I'm Roberg from Burbank High School, and today we're going to learn to solve quadratic equations using imaginary numbers. Let's start with this. Let's solve x squared equals 4. This means some number times itself equals 4. Now to solve this, we would take the square root of both sides, and we end up with x equals plus or minus the square root of 4. The square root of 4 means some number times itself equals 4. Well, it turns out that number is 2. We can check this by noticing 2 times 2 equals 4, and also negative 2 times negative 2 equals 4. That's why the plus minus is needed. Now let's try a different one. Let's try x squared equals negative 1. Now in this case, what number times itself equals negative 1? We'll start this problem the same way. Take the square root of both sides, and we get x equals plus or minus the square root of negative 1. What number times itself equals negative 1? Well, 1 times 1 is 1, and negative 1 times negative 1 is still 1. So this is kind of strange. It turns out that we have to use an imaginary number called I to solve this problem. X equals plus or minus I. I is a very interesting number, and it's very powerful in solving quadratics. Let's try another one. In this problem, we're trying to solve x squared equals negative 32. We'll start just like the others by taking the square root of each side, and we get x equals plus or minus the square root of negative 32. Let's rewrite negative 32 and see if we can find any squares. X equals plus or minus negative 1 times 16 times 2. Now the product of these three numbers is negative 32, but when written like this, we can clearly see that 16 is a perfect square. So we can pull out the root 4 and put it in front of the radical. So let's do that. X equals plus or minus 4 times negative 1 times 2. Now we need to deal with that negative 1. To deal with that negative 1, we pull its root out. Its root is I. So we're left with x equals plus or minus 4i times rad 2. And there's nothing more we can do with this. There's no more perfect squares we can factor out of the radical. So now let's talk about some properties of I, the imaginary number. Any number to the first power is simply itself. So I to the first power is I. Now remember, I is also the square root of negative 1. So we'll put equals square root of negative 1. What about I squared? Well, we can rewrite I squared as the square root of negative 1 times the square root of negative 1. And we get negative 1, because any square root times itself gives us the radicand, in this case, negative 1. What about I cubed? We can rewrite I cubed as I squared times I. Well, I squared was negative 1, and I was just I, so we end up with negative 1 times I, and that equals negative I. What about I to the fourth? Well, we can rewrite I to the fourth as I squared times I squared each of these I squareds is a negative 1, so we get negative 1 times negative 1. And negative 1 times negative 1 is simply 1. Let's do one more, I to the 5th. We could rewrite I to the 5th as I to the 4th times I. And let's see, I to the 4th was 1. 1 times I is simply going to be I again. And if we were to continue this with I to the 6th, 7th, 8th, etc., we'd actually notice a pattern. And the pattern goes like this. I, negative 1, negative I, 1, and then the pattern starts again with I. I to the 6th would be negative 1. I to the 7th would be negative I. I to the 8th would be 1. Now let's see how we can use this to solve more complex, or actually I to higher powers. Let's try I to the 20th. We could rewrite I to the 20th as I to the 4th raised to the 5th power, which would mean I to the 4th times 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 I to the 4th. Now I to the 4th is 1, so this equals 1 times 1 times 1 times 1 times 1. 1 times 1 times 1 times 1 times 1 is simply 1. Cool, so I to the 20th is 1. Let's try I to the 21st. We could rewrite I to the 21st as I to the 20th times I. Well, we just found out I to the 20th is 1. So this can be rewritten as 1 times I. 1 times I is I.